Hi everyone, let's get started with these announcements. This is the recorded class meeting that's for Monday the 28th of August. I regret that I am not able to be in class today, but as I previously announced, we're going to have these remote virtual recorded lectures for today, Monday the 28th, Wednesday the 30th, and September 1st, which is Friday. Also, as a reminder, if you haven't already submitted homework 1, you can take up until 12 o'clock noon on Monday the 28th to submit that. And then homework 2 is already available on Blackboard for you to begin. That is going to be due on Wednesday, September 6th by noon. Today's class lecture is related to economic equivalence and doing some example calculations having to do with the time value of money. This class lecture was recorded in a previous semester, so you may hear some student voices in the background. I may make some incidental references to times and places that don't match up, but you can ignore that and just be assured that the concepts are the same. The in-class exercise that I've emailed for you to go through during this class meeting is demonstrated at the end of the recording along with the solutions, and so I think you'll have everything you need to make this class a success. Feel free to send me an email if you have any specific questions.
Okay, so just a review of some of the terms that we've already addressed so far in the first 3 lectures. Remember that money has a change in value over time because of the effects of price inflation, and also because of the fact that when you loan somebody money now, you're having to put off purchases that you could have made. And so there's an opportunity cost built in there. And you're going to want more in the future because of the delay between when you're giving them the money and when you're receiving it back. And so the time value of money means that there's different value of money in different times. And so we have to label these variables. And remember that these notes are available as PDF files on Blackboard. And so if you want to print these out, it'll save you maybe the hand cramping of writing it all down. Of course, there's space in the margins for you to write additional information. But this present worth, there's different labels and terminologies that are similar. But we're just talking about a certain amount of money at time 0, meaning at the present. So how much money do you have now? And future worth is obviously going to be a single lump sum sometime in the future. And it's not defining how far in the future, it's just any time that isn't now would receive this label F as long as it's a single amount. And if there's going to be a recurring amount, then we call that an annual series or an annual worth, which is a consecutive equal end of period amounts. So we're going to look at some cash flow diagrams today and visualize how these labels are used. But this terminology is going to be important, especially when you start looking up formulas in your book, because the formulas will use these things like P, F, A, and so those will be amounts of money at some time in a cash flow diagram, either at the future, the present, or in an annual sequence. We don't talk about money in the past, though. There isn't like any sort of label that would indicate money that was some time ago. What you do is you just start your analysis at the first time that there was any kind of an exchange. You'd set that to be time 0, even if it was in the past. So if you saved money 10 years ago, if you made a deposit to a bank 10 years ago, then you'd make time 0 being that first time that there was an exchange between you and another organization or individual. Any questions about this terminology so far? Okay. Now, economic equivalence is this idea that even though the amounts may be different over time, that you can have an equivalence in value between money now and in the future by adding in the interest amounts. So someone gets paid for the privilege of you borrowing their money. If you're the borrower, you pay the bank a little bit extra in the future because you have inconvenienced them and you've delayed the purchase that they can make with their own money. And so economic equivalence is saying that when you factor in the interest, which is the accounting for the time value, that economically equivalent amounts can occur at the present versus at the future. So just as a specific illustration, because sometimes these concepts make the most sense when you hear it in the context of specific numbers. 100 is different from 110 in terms of like the number. We know that 100 does not equal 110. Those are two different numbers. But they're economically equivalent if your interest rate is 10% and the duration of the loan is 1 year. And so they're economically equivalent amounts because let's say price inflation is going up by 10% per year. Then that would mean you could buy the same amount of things now as you could buy 1 year in the future if you had 110 in the future. So we'll talk more about this idea of inflation later in the semester. But economic equivalence, one way to think about it is how do you maintain the ability to buy the same amount of things through time? And so maybe the interest rate would be related to the rate that prices are going up. So that's economic equivalence and one illustration of it. Here is how we substitute it into the formula, where the formula I think you've seen in some of the previous in-class exercises, future, so F equals the present amount multiplied by 1 plus I to the power of n. So here, n, the number of periods, is 1. The interest rate we express as a decimal, so 10% is expressed as 0.1, and then you add it to 1 because you're always going to get a return of your principal in addition to the interest amount. So the interest is 10% of the principal. When you pay back the loan, you have to pay the original amount and also a little extra. So that's why there's the 1 plus I on the inside of the formula. P was the amount at the present, which is times 0, and then F is the amount in the future, so 1 year from now. Okay, so any questions about how we've applied that formula? F equals P times 1 plus I to the n. So you use the interest rate and the time, the number of years, to find economically equivalent amounts. They're not equal amounts. It's just that they have the same value given a certain interest rate and a certain amount of time. Okay, now here are some of these labels. We've already seen P, F, A, and in previous class periods we've talked about N, which is the number of compounding periods, and I is an interest rate. So the lowercase I is a rate, meaning a percentage, whereas the capital I is the interest amount. So we distinguished between that in the first class meeting, where I is expressed as an amount per time. So that's what makes it a rate. Now, if we sketch it out as a diagram, this diagram would show that you're making a deposit at time 0. So this is a deposit of $100 now. And somewhere in a cash flow diagram, usually above it or beneath the cash flow diagram, you'd indicate what's the applicable interest rate, so 10% per year. And then you can see that this is just one time period, and these are defined as yearly time periods. And so here's time 0, which is the present, 1 year in the future. So the economically equivalent amount would be $110. Now, the arrow going down indicates that that's a deposit. The arrow going up indicates that it's a withdrawal. So it's money coming to you when it's the arrow up from your perspective. Arrow down means that you had to pay money. So you give the bank 100, you get back 110, and that exchange is economically equivalent at an interest rate of 10% per year. Now, remember, I'm not saying that 100 equals 110, and also the other thing is that a deposit and a withdrawal are different. It's just that the absolute value of the amounts are economically equivalent. So you kind of have to sometimes apply common sense that, you know, if you're making a deposit and you want to know how much can you withdraw, then the cash flow diagram would be up. But we're not talking about it being economically equivalent, just that, you know, a deposit and a withdrawal are the same thing. So this is an illustration about the magnitude of the amounts. And I think you'll get the hang of this as we work through today's in-class exercise. It'll help to reinforce the concepts. And I know I talked about this during the introduction and overview of the course, but part of the reason why it's so important for you to have these printed out is my idea is that you use these to work on the homework. That there isn't really going to be too many times this semester where you've got a homework problem that hasn't already been introduced with an in-class exercise. I know you've probably had other classes where you get the homework assignment and it's just completely unfamiliar. And it's like a different class almost. And I know how frustrating that is. And so my hope is that these in-class exercises are like a really smooth on-ramp to the assignments. And if you look carefully, there are clues in each one of these problems that informs later on how to solve the homework assignment. So if you have them printed out and you store it like in a 3-ring binder, then you should never be too confused when you're working on the homework. There's a couple of times this semester where, just to give you practice of solving something unfamiliar, I'll give you a problem that isn't directly related to an in-class exercise, but that'll be the exception rather than the rule. Okay, so let's apply this formula, F equals P times 1 plus I to the n, to solve this question. And just practice the labels. And so if you have the notes printed out, maybe you could identify what is P, what is I, what is N, what is F. All right, so you receive $100 in 1 year. So that's telling us the F is 100. N is 1. I is 0.1, because remember we express the interest rate in the formula as a decimal. So how much should you receive today? That's implying that P, the present value, is the unknown. So if we look at the cash flow diagram, you can either get the amount now or you can get it in the future. And so this, the cash flow diagram, both has arrows that are up, because it's not saying that you made a deposit. It's saying you just have your choice of get the money now or get the money in the future. And this is kind of similar to when people win the lottery. You know, they can either take a lump sum now or a series of payments through the future, and they have to make the decision which do they prefer. So here, the question is, if the interest rate is 10%, then what is the economically equivalent amount that you should get at the present? And I know it's tempting just to say, well, it must be 90, without actually plugging in the numbers, but that's not the case. We have to plug in the numbers because it's not just 90. And so let me give you a moment to do that. Does everybody have their calculator here today? Engineers, computer scientists, safety people should always be walking around with a calculator. If not in your hand, then in your pocket, or at the very least in your backpack. You got to be ready for calculation. So solve, what is P? Yeah.
What do you want us to do about rounding in this class?
Round to the nearest penny. Yep. When you've got a formula like this, there will be these situations in a few days where you will round based on the how many digits are in the factor. That'll make more sense, but as a general rule, round to the nearest penny. Okay, so we have F is 100. 1 plus I is going to be, let me just write this out. So 100 equals P 1 plus I, so 0.1, to the power of 1. So that's basically 100 divided by 1.1 is equal to P. Okay, so if you go through that process, did anybody else also get $90.91? Okay, very good. So one of the things that's a dangerous idea is sometimes people feel like they understand the formulas and that's all this class is about. But this class is partly about plugging numbers into formulas, but it's also interpreting problem statements. So you're going to get better and better through the semester, like reading these problem statements and being able to like figure out what they're asking. It may seem a little unfamiliar at first, but probably if you ever took like an ACT prep class or an SAT prep class, they trained you in how to break down those problem statements, because there's only, you know, a few of the logic games and types of questions, and so you'll get better at this. But my point is don't fall into the mental trap of thinking just because you've got the formulas on an equation sheet that you're good to go. It's actually as much about interpreting these unknowns and problem statements as it is putting the numbers into the calculator. Okay, there is a convention, or just kind of like an accepted way of visualizing and summarizing these problems that you need to become familiar with. And so here's a cash flow diagram. And remember, the way to interpret this is if the arrow is down, that means that you're paying money. And if the arrow is up, it means you're getting money. So assuming that this perspective is talking about you. It could be about a bank or a business or your uncle or whatever. But this is saying that from whoever's perspective it is, there was a deposit of $11,000 at time 0. And so we want to know, for a given interest rate, how much can they withdraw in 3 periods? And these may be monthly periods, they may be years. It's just however frequently the interest is compounding. Now, the way that we know this is an unknown is it's a dashed line and, of course, the question marks. And so the convention, you need to look at this and be able to say that this is find f given p. And so as a ratio, this is f in the numerator and p in the denominator. And if you've got the book, in the back of the book, there's just page after page of tables. Does anybody have the book here today? Anybody got it handy? Can I just open that book up and show people for a second? Because part of the reason why, thank you very much, part of the reason why you need to understand this convention is that there are factor tables in the back of the book that you can use for problem solving. It's these ones that have the blue printing on it. So there's a 16% table, a 14% table, 11. So it's just basically solved a lot of time value problems at different interest rates. And so it simplifies the calculations when you can use these tables. Thank you. And but to use those tables, you have to understand how to break a problem down into the ratio. So what I'm saying is, when you see a problem like this where f is the unknown, that is find f given p, or f slash p. F in the numerator, p in the denominator. This is the opposite. Present amount is the unknown. Future is given. So this is find p given f. P in the numerator, f in the denominator. Okay? This, remember, an annual series is where the amounts, the recurring amounts, are equal. So the arrows are the same length, which is an indication that the amounts are the same every year, and there's no gaps between periods. So it's consecutive. So this is an annual series, and so this would be, the A is the unknown, so it's going to be find A given P. So A in the numerator, so A slash P is how we'd say that, and when you go to the factor tables, you'd find the column that has A slash P, and then you'd be able to use the factor for your problem solving. Finally, this is find P given A, where A is the known amount, and the unknown is what's the present value. So this is another thing that you'll just develop the familiarity over time, but I wanted to give you the idea that there's kind of an accepted convention or a notation that we follow for this.
So with the 3 arrows and it says 12,500, does that mean like 3 times 12,500 or like 12,500 divided by 3?
Good question. That means each year is 12,500.
Okay.
Yeah.
And also, would you need the interest rate to actually find the answer?
You would, yeah.
Okay.
Yeah, to actually be able to solve for a numerical value, you'd need the interest rate. Great questions. Are there other questions? I know we've got a big group and it can be intimidating to interrupt or ask questions, but please don't. I think that things are going to get pretty relaxed in here, especially because of the time we spend with the in-class exercises. It's always a little awkward at the beginning of the semester. You don't know the professor, you don't know the other students so well, but it's going to get relaxed in here, and so hopefully you'll feel comfortable to ask questions when you've got them. What we're going to do now is spend some time with in-class exercise number 4, and I've printed out about 30 of these, but I'm hoping that at least 10 of you have already got them printed out for today. Good.
I already have 4 from 6 printed out.
All right, excellent. So I'm going to pause my recording and okay, so let's go through the first 3 problems, and you can collaborate. I actually hope it gets really noisy in here as you're working on this, because that means you're talking, you're thinking, like the noisier it is, the happier I feel during the in-class exercises. I told you in the overview of the syllabus that when you're doing homework assignments and exams, I want it to be your work, but these I really want to be as collaborative as possible. So the first 2 problems are kind of just applying these ideas of economic equivalence, and then the third problem is a little bit more of a, like a mental analysis. And I don't want to say too much about it because I want you to go through the process of figuring this out. But let's just do the first 3, and then we'll go over the solution together, address any questions. I'm also going to be circulating around with the answers as you're working on this. So if you just want to check your answers, then I'll tell you thumbs up or help you if you have a question. But then, if you do finish early, you can get started on the 4th one. But I'm going to interject with the solutions to the first 3 before we collectively go on to the 4th one together.
So since
Let's take a moment to look at the solution to these first few problems and make sure that we're all on the same page, so to speak. Let me try and make it a little bit bigger. Now remember, if you don't quite finish an in-class exercise, you don't need to panic because the solution will be recorded in the video that's posted on YouTube. So you can finish this up after class if you kind of feel like you felt behind on a certain thing. Okay, so this first one, the owner pays $550,000, and that's the first transaction we hear about, so that's at time 0. So that's a present value amount, and the arrow is down because it's an outflow, meaning a payment. And then there's $85,000 of extra revenue for each of 6 years. So there's 6 arrows with 85,000, so 1, 2, 3, 4, 5, 6. And then in the 6th year, the machinery is sold as scrap. And when you sell it as scrap, that means you're getting more revenue on top of the revenue you got for operating the equipment in the 6th year. So there's just this second amount of $50,000 that's on top of the annual series. So there's 2 ways you could depict it. You could either say that this is an annual series that goes through 6 years, or if you wanted to, you could always combine it as a lump sum so that there's an F of $135,000 at year 6, and the annual series only goes through the 5th year. Numerically, those would be the same. But are there any questions about this cash flow diagram? And it was from the company's perspective, and so we were just looking at it as it would appear for them in terms of outflows and inflows. All right, so that's the first problem. Second problem, you want to receive $95,000 next year. So that's defining for us when is the present and when is the future. So next year means that it's 1 year from now, you want to have $95,000. So future value, $95,000, you want to receive it, so that means it's up because you're going to get the money. So how much should you deposit today means that the unknown is an arrow downward, so P equals unknown amount. So here's the cash flow diagram that illustrates it. You should just put the interest rate somewhere, to the side or below. And then here's our formula for it that we can use to find out that the amount you should deposit now to make sure that you've got $95,000 in 1 year is $87,155.96. So when you solved it in your calculator, the decimals continued on and on beyond the nearest penny, but for our purposes, the nearest significant figure would just be the penny, so it's 96 cents. So any questions about the second one? Okay. Now, the third problem's a little bit tricky, so let me just summarize the options you've got. You can either put your money in the bank, or you can buy the fuel and store it, because what you want to do is have 100,000 liters of fuel available 3 years from now. And so the question is, should you buy it while prices are cheap and then pay to have the fuel stored, or is it better to just deposit however much you would have spent on fuel and then have that number of dollars available in the future to buy the fuel at whatever the price is in the future? So how much does it cost if you buy now? So if you buy now, you'd have 100,000 liters of fuel at $2.20 per liter. So that's $220,000 for the fuel cost plus the $13,333 per year for 3 years. So the total amount that you would have to spend is essentially $260,000 if you wanted to buy the fuel now and then cover the cost of storage. So part B is saying, if you take that money and invest it, then what would the situation be? You know, find out how many dollars you've got in the future, what number of dollars is available, and then how much would it cost to buy the fuel at this higher price, where the price is $2.65 per liter. Okay, so the first part of that is to find out how many dollars are you going to have in the future. So if you take essentially $260,000 and you put it in the account for 3 years and don't make any withdrawals until the end of the period. So we're finding how many what's the number of dollars in the future. So F equals what? And you can see the substitutions I've made. I think it's a good idea in your homework to write out as many steps as you can. Like, show your calculations is the point that I'm making. Because if you make a mistake, you'll get more partial credit if you show your calculations. And so here, 1.07 to the third power. If you actually do that calculation, what's inside of the parentheses is 1.225043 and so on and so forth. So I'm showing as many steps as possible just in case the grader has any uncertainty about what was done. So you have $318,000, but the fuel only costs $265,000. So option B is better. If you take that money and put it in the bank, not only can you buy the fuel that you need, but also you'll have $53,000 left over. So the question, should you buy the fuel now or buy the fuel in the future? In this particular case, the answer is buy the fuel in the future. Okay, on the back side we had the third problem, or problem 4. All right, let me show you how this one works. You maybe haven't looked at it yet, but let's talk through it together. How much should you pay in year 4 if you receive 4 equal annual payments of $12,500 each, as shown below? Now here's our cash flow diagram, and what I did was I labeled each one of these arrows, because what we want to do is find out what is their individual contribution to a certain amount in year 4. So for example, the $12,500 that's at the end of the first year, I'm calling that arrow A. If I want to find out how many dollars does that compound to at year 4, I'm going to do n equals 3, because it's 1, 2, 3 years in the future. So the amount of the $12,500 in year 1, if you compound it into the future to the 4th year, it becomes $14,470. And then we follow that same pattern with the other years, where this arrow at year 2 is only 2 years away from year 4. So I'm compounding it. The n is 2. And so that individual $12,500 amount compounds up to $13,781 over the course of 2 periods of compounding. And then a similar process with this amount at year 3. Now the $12,500 that is, I've got the labeled D on that, that's already at year 4. So I don't have to do any calculations with that. It's already in the fourth year. And so if you add up all of the amounts that have been compounded into the future, the equivalent value is 53,876. So what we've done essentially is we've moved the money forward in time to find the equivalent value. So you can either take 12,500 each year for 4 years, or what's the lump sum amount 4 years in the future? Or if you received these, how much would you have to pay back to bring it into balance, is what this is asking. So the amount that you'd have to pay as a lump sum, 53,876. Now this is the form of find F given A. The fourth payment is in the same year as the outflow. It's kind of strange for a find F given A that the annual series is in the same year that you're paying it back. But this equation would allow you to solve for the same amount but just a different way. This ratio on the right hand side here, that's find F, where you're multiplying the A of 12,500 by the result of this. So if you do that, then you'd get the same 53,876.